There's a hard limit to how much an AI model can hold in its head at once. It has a name, the context window. And understanding what it is, not just the fact that it exists, but why it works the way it does, explains a whole set of behaviors that otherwise seem random. Why does ChatGPT seem to forget things it told you earlier in a long conversation? Why do models perform worse on tasks buried in the middle of a long document? Why does pasting in a huge amount of text sometimes make the model less accurate, not more? All of these connect to the same underlying constraint. Let's start with what the context window actually is. When you interact with a language model, everything the model has access to in that moment, your messages, its previous replies, any system instructions, any documents you've pasted in, all of it has to fit inside the context window. The context window is the model's working memory. It's the total amount of text the model can process at once. It's measured in tokens. You've heard that word before. Tokens are the chunks of characters the model actually works with, roughly 3 to 4 characters each on average, meaning a token is shorter than a typical word. A context window of 128,000 tokens holds roughly 100,000 words, about the length of a full novel. That sounds large. For some tasks, it's still not enough. Here's the key thing to understand. The model doesn't have a memory outside the context window. There's no background file that gets updated as you talk. There's no persistent record of your name, your preferences, or anything you said last Tuesday. When a new conversation starts, the model starts from zero. What you see in the chat window is literally everything the model knows about your conversation. When old messages scroll off or get truncated to save space, they are gone from the model's awareness entirely. This isn't a design oversight. It's a consequence of how transformer models process information. Transformers work by computing relationships between every token in the context and every other token. That's what gives them their ability to understand meaning across long distances in text. Any word can directly influence any other word, but it also means the computation scales with the length of the context. Double the context and the computation more than doubles. There are hard engineering limits to how large a context window can practically be. The way to think about it is this. Every token in the context window can see every other token. They're all in the same room, influencing each other. Tokens outside the context window don't exist. They're not in a waiting room. They're not in a compressed summary somewhere. They're absent. This explains the forgetting behavior perfectly. If your conversation is long enough that early messages are being dropped to fit within the limit, the model has genuinely lost access to them. It's not pretending to forget. The information is no longer present in its input. There's a practical implication here that most people don't think about. When you're using a long context model and you paste in a large document, you're not just adding information. You're using up space that could otherwise hold your conversation history or additional context. Every token you put in competes with every other token for that fixed amount of room. Strategy matters. Pasting irrelevant text doesn't give the model more to work with. It dilutes the signal with noise and pushes other useful content toward the edge. Now, what does the model actually do with everything inside the context window? It processes all of it together simultaneously. When you ask a question at the end of a long document, the model's answer is influenced by every token in that document, the beginning, the middle, and the end, all at once. This is very different from how a human reads, which is sequential. A human reads from top to bottom and builds up a mental model as they go. A transformer sees everything at the same time. That sounds like an advantage. In some ways it is, but it also creates a specific weakness. Research has consistently shown that models perform better on information that appears near the beginning or end of a long context, and worse on information buried in the middle. The term for this is the lost in the middle problem. There are two main approaches to getting past context window limits. The first is just making the context window bigger. Models have gone from 4,000 tokens a few years ago to 128,000 tokens, and some experimental models have pushed into millions. The engineering challenges are significant. The computation cost grows fast with context length. But this is an active area of investment. The second approach is retrieval augmented generation, or RAG. Instead of trying to fit an entire document collection inside the context window, you build an external database. When a user asks a question, A separate search step finds the most relevant chunks from that database and inserts them into the context. The model never sees the whole document library. It only sees the pieces most likely to be relevant. This is how many enterprise AI applications work, and it's why they can answer questions about internal documents that never made it into the model's training data. Both approaches have limits. Larger context windows are expensive to use. Every token in the context costs compute on every forward pass, so running a model with a 1,000,000 token context is dramatically more expensive than running it with 10,000 tokens, even if you're only asking a short question. The cost scales with what's in the window, not just with what you asked. RAG depends on the quality of the retrieval step. If the search misses the relevant chunk, the model never sees it. Neither is a perfect solution to the fundamental constraint. There's also a third thing worth knowing. Context windows reset between sessions, but modern AI products increasingly add a separate memory layer on top. This isn't the same as the context window. It's a database that stores summaries of past conversations, retrieved and inserted into new sessions. When a product says it remembers something about you, this is usually what's happening. Not a longer context window, but a separate retrieval step that adds your history back in. Understanding this distinction matters practically. The model's actual working memory is still bounded. The external memory layer is a workaround, not an expansion of that bound. It can help, but it's not the same as genuinely persistent memory. There's also a subtlety about how context position affects model behavior, beyond just the lost in the middle problem. Instructions placed at the very beginning of a context, in the system prompt, tend to be followed more reliably than instructions buried later in a long conversation. The model attends to the beginning strongly, then to the end, then weakly to the middle. This means that if you want a model to follow a specific format or rule throughout a long interaction, repeating the instruction at regular intervals is more reliable than trusting that a single early mention will persist. The context window doesn't decay the way human attention does, but the model's effective attention across that window is not uniform. Here's the frame worth keeping. A language model processes a finite window of text, simultaneously, all at once. Everything inside that window influences the output. Everything outside it doesn't exist. There's no memory, no accumulating knowledge, no awareness of anything that came before the current context. This one constraint explains the forgetting behavior, the lost in the middle problem, the cost of very long conversations, and the reason retrieval systems exist. It's not a quirk, it's a structural property of how these models work. As context windows grow larger and memory systems improve, some of these limitations will ease, but the underlying architecture will stay the same, a model that knows only what it can see right now, working as hard as it can with exactly that. If that kind of precise mental model is what you want from AI content, subscribing is how you get the next one.